Okay, yeah. So thank you for the kind introduction, and also thank you for the opportunity to present in this online lecture series. So as Joachim said, my name is Greta Lindwall, and I work at the Department of Material Science and Engineering at KTH here in Stockholm. And in the presentation today, I will show you some of the past and ongoing work that we've done in my group with the focus on microstructure evolution during additive manufacturing, and in particularly focus on microstructure evolutions in steel during powder bed diffusion techniques. But before I begin, I would like to acknowledge my co-authors and collaborators who has contributed to this work. So both current and former colleagues at the KTH, but also industrial partners and collaborators at research institutes. And I would also like to acknowledge the primary funding sources that have supported this work. Okay, so the AM research we do in my group here at KTH focus on or falls within three of these four core pillars of material science. However, the main focus this far has been on understanding the connection between process and structure. So we combine experimental work with computational modeling to understand how the microstructure evolves, both during printing and as well as during post-processing of additively manufactured materials. So while we do a lot of experimental work, then most often the main motivation is to generate the data or the information that we need to develop or validate the computational tools. Because in the long-term goal is to have the computational tools that are needed for computational materials science. So most of our projects are motivated by developing these tools. And in particular, we have focused on computational thermodynamics and kinetics and so-called CALFAD-based models, since these are can be made multi-component, so we can apply them for multi-component material systems. So calculations for real materials with many alloying elements. So we can use them to predict how things change with composition and process conditions, which is key for computational materials design. So emphasis is then on microstructure modeling and computational thermodynamics and kinetics. But we have also done a lot of experimental work for the model validation or to understand what we need to model. And in this presentation, I will include quite a lot of examples then of how we have used in situ synchrotron X-rays to follow the microstructure evolution during AM processing, as you will see in this presentation. Okay, so I've structured the presentation into three parts. And the central theme is additive manufacturing of tool steels. So I will show examples of tool steels. So first I will focus on the laser powder bed fusion process. And then after that, I will talk about the work we've done to develop a sample environment that we need to study the electron-beam powder bed fusion in situ using synchrotron X-rays. And then the third part will be then when we use this sample environment to again look at this tool steel. Okay, so the tool steel then that have been in focus is a hot work tool steel. So these steels are developed for applications at high temperature. It could be, for example, high pressure die casting of aluminum. And when you have these high temperature tooling applications, then you need a material with good yield strength, good toughness and ductility, and also good temper resistance. And these are of interest for additive manufacturing then, since you could do more complex tool shapes with the help of AM. For example, incorporate internal cooling channels and improve tool life and function performance of the tools. And conventionally, these tool steels then would be manufactured by electroslag remelting. So you would you would get a coarse solidification structure, and this is then exposed to a number of thermomechanical treatments, and then it's exposed in the final step. It's exposed to like a hardening treatment. So during the hardening treatment, then you would heat the material to the temperature where austenite is stable, and then you would cool, quench the material with high enough cooling rates, then so that martensite can form. So you have a martensitic structure, and this you then temper at a rather high temperature so that alloying elements can diffuse and form carbides or secondary carbides, which contributes then to the strength of the material. But this is how it's done then conventionally. But then if we look at additive manufacturing, and particularly in this case, laser powder bed diffusion, we have a very small melt pool, or the laser creates a very small melt pool, and the material in the melt pool would solidifies really fast and then is exposed to really high cooling rates. So during this then formation of martensite is possible already during the process. So the question thus arises whether we actually need this full hardening treatment that I showed you on the previous slide, or if one can just take the as-built material directly and temper it. So that was something that we've studied in this project. And the first thing we looked at was then to see how the as-built microstructure looked like, and if we can use then the computational tools to predict the as-built microstructure. So if we start by looking at the as-built microstructure then, so here you see two SEM images of this material. So we can conclude that we have a mainly martensitic microstructure. So we look at the image here to the right in higher magnification. We can see that we also have a solidification substructure, so that alloying elements have segregated to the boundaries here. And if we look at these STM-EDS maps, we can also see that it's mainly vanadium, molybdenum, and chromium that segregates or are enriched in these segregated regions. But we can also see that we have some carbides in the junctions, where there's richer in molybdenum and vanadium, which are probably then formed during solidification. So we know that the as-built structure after laser powder bed diffusion looks like this then. So the first one thing we wanted to do was then to see if we can use the computational tools to predict the structure and capture this segregation then during solidification. And for this we used the diffusion module within the thermocalc software package, so DICTRA. And DICTRA solves the multi-component diffusion problem in one dimension. So in order to do a simulation with DICTRA, then we need a CALFAD input. So we need the thermodynamic descriptions, and we need the diffusion mobilities. And DICTRA assumes a sharp interface. So in the case when we want to do a solidification simulation, you would start with a computational cell then that is fully liquid at a high temperature. And then as the temperature is decreasing, then a solid phase can form, and you create this interface here, which you can then follow during the solidification. And another input that's needed for this simulation is the size of this computational domain. And this is something that, in this case, we got from experiments. So it's around 600 nanometers. And then another input that we need is also the thermal history, or the cooling rate during solidification. And also, when we do these simulations, we need to define what phase forms. So in this case, with the laser powder bed diffusion, then we know we have very high solidification velocities. So we were not sure then what phase should be the first phase that forms in the case of this material. Because if you look at the equilibrium situation for this composition, so here are the equilibrium phase fraction as a function of temperature. So at high temperature, you can see that the first solid phase to form is the delta ferrite, and then austenite comes after. So if we believe that this holds during solidification, delta ferrite should be the first phase to be added here then during the simulations. But this we weren't sure about, and also if we look at the as-built microstructure in SEM and EBSD, we couldn't see any signs of delta ferrite. So there was no delta ferrite in the as-built microstructure. But if we do one Dijkstra simulation, allowing delta ferrite to be the first phase to form, we can see that it forms, but then also that it transforms to austenite before solidification is finished. So we cannot, from just post-characterization, say whether we had delta ferrite present during the processing or not. So for that reason, we looked into solidification models or models for dendrite growth kinetics, so the KGT model, to see if that could help us then understand the solidification path in this during processing of this steel. So in this model, then we can get we can include the solidification velocity or the effect of the rapid solidification velocity by using a velocity-dependent partition coefficient and liquid slope. So this model will then give us the dendrite tip radius, composition, and interface temperature. And this has been used to predict well structures, but also in additive manufacturing then to predict the solidification path. So in our case, then we did these calculations for both the delta ferrite phase and the austenite phase. You can see the results here as in terms of the tip temperature. So if you're at the lower solidification velocities and you're at the high temperature go down, then delta ferrite has the highest tip temperature and would then be expected to be the first phase to form during solidification. But then if you go to higher solidification velocities, one see that it's a shift, and it's the austenite that has a higher tip temperature and would be the primary solidification phase during solid phase during solidification. So we had the possibility then to validate or to evaluate this model then using in situ synchrotron X-ray diffraction. And to generate the solidification conditions then that we were interested in, we have used two different sample environments. So first we did measurements at argon photon source using this sample environment that's called AM replicator. And then we also did measurements at with the PSI at SLS with this sample environment that's called mini SLM. So they're quite different then, but here you have more like a transition mode measurement and solid plates that you melt with the laser, and the laser power is lower, somewhat lower than in the mini SLM case, and also the speed is lower. So here you would result in a larger melt pool and slower solidification conditions. And in the mini SLM, then you have conditions then closer to the real powder bed fusion process. So you have in this case a laser power of 300 watts and a scanning speed of 0.6 meter per second. So here we would then expect much faster solidification conditions. So from these measurements, then we can get this. We can acquire this data then in terms of the diffraction patterns. So here you have the diffraction patterns as a function of time then. So here, in the case of the EM replicator, is where the laser melts the material. So it's we have liquid, no signal. And then as the temperature goes down, then or as it solidifies, one can see then that the delta ferrite is the first phase to appear and then disappear. And then we have austenite transforming. And this can be then compared to the mini SLM, where we had faster solidification behavior. And here we did not identify or did not detect any delta ferrite, which then suggests that austenite was the first solid phase to form. And from these diffraction patterns, we can also extract the cooling rates, or how temperature changes in the phase. So here are those plots, the temperature, the cooling rate as a function of time for both measurements. So if we then look at the AM replicator, we have a cooling rate of around minus 20 Kelvin per second, according to the diffraction data. And in the mini SLM case, we have a much higher solidification cooling rate, so over 1 million Kelvin per second. And using some thermal modeling, in this case, we used Rosenthal, so the classical analytical solution to estimate the temperature distribution around a moving heat source. We can then get from the cooling rate to get the thermal gradients and the solidification velocities. So in the case of the AM replicated, then the solidification velocity is in this range. And for the mini SLM, where we have the faster scanning and higher power, we had faster solidification velocity. So this we can then compare to our tip temperature model, or the KGT model. If we then put in the values we got from the measurements with the AM replicator and the mini SLM, they are here then. We are on different sides of this cross point, and we observe experimentally what we expected from the modeling. So based on this then, we could set up our Dictra calculation, and now we then knew that these high solidification velocities that we have during laser powder fusion, we expect the delta ferrite to be suppressed and the austenite to be the first primary phase to form. So we define this phase then to be FCC. And then we can perform this calculation and follow then at the interface how the elements move, and we get this then, the lines here. Here is the calculated segregation profiles. So here is the boundary, and here is in the middle of the solidification structure. So we can see then, as we expected from the experiments, that molybdenum segregates a lot, vanadium and chromium. And then we've also done EDS scans in TEM to compare with, and we can see that we are in a good agreement with the simulations. So even if the simulations is a simplified model of what the solidification that happened during laser powder bed fusion, we can still use it to predict the segregation trends during AM processing of this material. And then we also have within the thermocalc software package models for calculating the martensite start temperature. So we calculated the martensite start temperature then as a function of this segregated composition profiles that we have for different austenite grain size. And then we can see that here in the segregated regions, due to the enrichment of those alloying elements, we have a decrease in the martensite start temperature. And if we assume then that a build temperature, we had a build temperature around 200, one would can draw the conclusion that maybe we cannot have fully martensite in the full structure. And that would also explain why we see this retained austenite in this segregated structure, segregated regions. So that was the first part on the microstructure evolution during a laser powder bed fusion of this steel. So next we would like to also see how we can do this for electron-beam powder bed fusion. But for this, we need a sample environment that can handle this. And we have had a project where we have developed and constructed a sample environment for this. So I will present this work and show some of the capabilities. So as I said, as I showed, there's several options available for in situ X-ray studies of laser, so many sample environments for laser AM. But when we started this, there were not any options available for electron beam powder bed fusion. So it's important to understand a lot of the knowledge gained through the in situ work on laser can of course be translated to electron beam, but not everything. No, it's fundamentally there are two very different processes. First of all, you have a different heat source. So the laser just is photons just interacting with the very top of the surface, whereas with the electron beam you have electrons that interact much more with the material or much deeper into the material. And then you also have different processing conditions. So you have different processing atmospheres. So in laser powder bed diffusion, it's usually performed in inert gas, whereas electron powder bed diffusion is in vacuum. And then you also preheat the powder bed to high temperatures to sinter the powder bed, which you normally don't do then in the laser powder bed diffusion. So the process, the powder bed diffusion, the electron beam powder bed diffusion process is at a much higher temperature. And also, but otherwise you have the same processing steps, but then with the extra preheating and post-heating in typical for EBM then. And then you have the same defects as you would see in laser powder bed diffusion, but in electron beam you also have this process instability that's called the smoke effect, which we will come back to a little bit later, which is interesting. So there's some extra constraints or things to that has to be accounted for when developing or constructing a sample environment then for electron beam powder bed fusion. But in this project then we've developed this mini melt, which we call it, and it's based on the commercial machine, Freemelt 1. So it has all the same process steps as you would have in the commercial machine, so that we can do operando measurements. So the electron gun is the same, exactly the same as in the Freemelt 1 system, but then we had to do adjustments or customize it so that we can have it at beam lines. So the weight had to be reduced and the height, and also we needed to have a solution for the X-rays to be able to go through so we had to have X-ray transparent windows that could still maintain the vacuum at high temperature. But it looks like this, and it's then called mini melt. So the main difference then is that we have customized the process chamber or the vacuum chamber, so it's much smaller than in the commercial machine. The build area is only 5 centimeters, or the build start plates are 3 centimeters. And then we have this behind this heat shields here, there's the X-ray window or the Kapton window. But otherwise it has the same function as the real process, the real commercial machine. So we can simulate all the process steps as you can in the real, in the commercial machines or in the full scale machines. And then we had, well, the previous work I showed you on the laser side, we had different types of sample environments. So it was the AM replicator with the solid plate, which you melt with the laser. And then it was this more operando type where you print a small volume and then you tilt it and can do like reflection mode measurements. Then for the laser side, I have also seen many times they use like sandwich kind of structure. So one has some material that can keep the powder bed very thin then, so to allow for transmission mode X-ray studies. But for the electron beam process, we couldn't really use any of those types of sample environments since we have this really high process temperature. So if we would confine the powder bed just into very thin between two walls, we wouldn't be able to get the thermal conditions that are of interest for the process. And we would also affect the melt pool dynamics by the walls. So for this reason, we developed this concept unconfined powder bed, which you can see here. And here we make use of the fact that we can shape the powder bed. So we have customized rake blades then that can shape the powder bed. So you have a powder bed, but it gets thinner and thinner. So you get like a hill, which is then thin enough for us to look through with the X-ray beam. So it looks like this then, the powder bed, and then after printing then we would print this wall. But we've also tried to do small squares, so cubes, and then it looks like this. And it looks like this then in the machine. So we shape the powder bed, so we can look in transition mode with an X-ray during processing. So by using this concept unconfined powder bed, then we can include all the steps, study all the steps like preheating and a sintering step, and then also have it at high temperature. We can have this powder bed at high temperature, and we can also do multi-layer and more complex scan patterns, and also probe below the surface if we're interested in that, and not just the surface as you would do with the reflective mode sample environments. And this mini-melt then is compatible with the Swedish beamline or the Swedish material science beamline, P21 at DSC, at Petra 3 synchrotron at DSC, and also at the white beam engineering material science beamline, P61A. So that's where we've done our experiments. So we've done, here is the mini-melt. So we've done imaging or radiography at P61 and diffraction and scattering at P21. So I'll just show you some examples then of the capabilities of this sample environment. So here is first then some examples of in situ X-ray imaging showing the melt pool. So here we melt the powder hill then, a line, 5 layers at 6,600 kilohertz. So the gray values then are correlated with the X-ray transmission of the material. So it's the electron density. So we see the density contrast and how it changes then as the electron beam melts the powder. And I have here still images of this. So here's first the schematic showing them. So we have the powder hill, and then the melt pool, and then the electron beam will melt some of the powder, so the green parts, and then there will be still like powders on the side that we will see. And here is some processed images then, which shows the difference between the frames before arrival of the electron beam and the current frame then, so it's more the dynamics. So here we can then see the melt pool and its dynamics, but also spatter, and determine spatter velocity, size, and directions, and so on. So this can now be used then to study the electron beam powder bed fusion process. And here is some examples then for nickel-based alloy, which Erlangen, Nick Semyaton in Erlangen is working with. So here is the melt pool then, and it's how it varies depending on the process conditions. So in the first part here, it's pure conduction melting of the powder, so no vapor depression. Here on the second one, you have this vapor depression during the melting of the powder. There's not keyholing yet, but clearly evaporation driven. And then here in the third one, now it's this keyhole formation in the powder bed. It looks like this in our case. And then They've also used it to look also for nickel-based alloys then. They've looked at cracking. So here one sees crack, that the crack is opened here and filled with molten metal. And then the third example I have, or last example I have of the imaging is then this smoking effect that one has, that can happen during electron beam powder bed fusion, or it's a process instability. You don't want that to happen, and that's you can see the still images here. So we have the electron beam melts a single point in a powder bed. So we have a nickel-based superalloy again. So in the first image here, then the image is the electron beam is turned on and on the surface, and then on the image here, then you can see that some aggregates start to form, or there's some melted material aggregates. And then on the C and D image, you can see that the some evaporation-driven repulsion of particles from the area where the beam has impacted. Also, and then in E and F, there is a rapid repulsion of the powder particles due to electrostatic discharge of the charged up powder particles. And then if you look at an X-ray imaging video of that, then it would look like this. So you have the aggregates forming, and then the repulsion. And this is called smoking then, and it's a process instability. It stops your process. So this is something you want to avoid. So by learning more about the powder bed behavior using this mini melt, one could perhaps then adjust or optimize the process so that one can avoid these kind of process failures. So that was 3 examples then of the radiography. Next then we will talk more about the diffraction or wax. So this is the same then, similar to what I showed you in the laser X-ray studies. So we have the electron beam then melting the powder bed, and then we get the diffraction patterns and how they evolve with time. And since we can then repeat or simulate all the process steps during the printing, we can also record the diffraction patterns then throughout a printing cycle. And one example is shown here then. So we have first the recoating. We can see that here the powder bed is preheated, or here comes new powder, and then it's preheated. Then there's nothing happens. Here is ramp up of the E-beam. Here is the melt line then. And then there's post-heating. And then the rate blade came with a new powder later. So with this, we can follow how the material behaves then throughout the full printing cycle. Okay, so that was then the second part of this. So the development of this sample environment for electron beam powder bed fusion. So next, we will then use that to continue looking at our tool still. So if we come back then to this direct growth kinetic model, or the KGT model for this material, we saw that for the laser powder bed fusion process conditions, we expect to be in this higher solidification velocity range. But then for electron beam powder bed fusion, we know the melt pool is larger, and the solidification cooling conditions are slower. So if we look in our diffraction patterns, then we can identify delta ferrite during after melting. So we know that delta ferrite forms and disappears. And if we extract the cooling rates from these patterns, here in the case of electron beam powder of 480 watts and scanning speed of 100 millimeter per second, we can get a cooling rate of around 1000 or 1500 Kelvin per second. And that would then correspond to a solidification velocity that is around 0.03 meter per second. And so we would be definitely on this side then of the we would expect delta ferrite to be the first solid phase to form. But then with the electron beam, we have a large potential to change the parameter and perhaps affect how the solidification condition or to vary them. So to do that, we try then to print with different powers and beam velocities and do this extract the obtain these X-ray diffraction patterns. So from these different electron beam parameters, then we will get varying cooling rates. So we use that then. We did then the X-ray measurements then for these different process conditions or different powers and scanning speeds, and then we measure then for how long the delta phase was present during the solidification. So we got like a delta phase time, or what you want to call it. So we did that for all these different process conditions then, and you can see here then the results of those. So this is the time delta ferrite is present during solidification as a function then of the cooling rate. And this is done by the with the in situ synchrotron X-ray studies or measurements. And then we wanted to also see if we could use the solidification or the solidification simulations with Greta. So here now in this case then we know delta ferrite is the first phase to form then, so it's a peritectic solidification. So we first have to have the delta ferrite coming, and then austenite will form at some point, and we will follow both these interfaces during solidification. So here we need again then the thermodynamics and the fusion as the input, and we need the computational domain size, which we took from experiments, and then we also need the thermal history then, which we then have from our process simulations. And here is then the results for the Dictra simulations if we have a cooling rate of 1,400 Kelvin per second. So here is then the phase fraction as a function of time. So here at 0 then it's at the liquid, so where everything is liquid, and then we can see the delta ferrite forms and it starts to disappear, and then austenite starts to form. And then we can also see that ferrite reappear after some time due to the segregation and temperature that we have reached during cooling. So if we just look at the ferrite then and assume or define like the time ferrite is present, we get this value then for this cooling rate, and then we can do these simulations for several cooling rates. So here for a higher cooling rate, so 2,700 Kelvin per second, and then we can see that the time the delta ferrite is present during solidification is shorter, and then we can do this for the solidification velocities of interest and see how the delta ferrite time decrease then with cooling rate. So this is for the experiments, but then if we compare that with what we simulated with Dictra, we get a good agreement, which is again suggesting that we can use these tools then to understand what's happening during the process, despite the model being a simplified model. The reality is more complex than the model. This was what I had planned to present today. So to summarize then, we could see that the primary solidification phase vary depending on thermal conditions, and that we have delta ferrite as the first primary phase if we process at conditions typical for electron beam powder bed fusion, but at laser powder bed fusion it's suppressed, and we have austenite as the first solid phase. And then we can conclude that we can use these computational thermodynamics and kinetics tools to understand what we see in this AM structures. And then I've also presented this minimal sample environment, which has then been developed and implemented and shown how it can be used for high-speed X-ray imaging and diffraction measurements of the electron-beam powder bed fusion process. Thank you. With that, I'd like to acknowledge my collaborators again and say thank you for listening.